If you've ever wanted to make, say, a game without learning complex code, you've probably heard of Scratch. It's a visual programming language primarily aimed towards children and teens, where you build games, animations, and stories simply by clicking blocks together. There is a whole community on Scratch's website which has shared over 1.3 billion projects over time and is very active, making original projects and clones of pretty much any software you can think of. The important thing about Scratch is that it's a very limited engine meant for creating simple stories and games. Of course, that has not stopped the community from cloning games with more complex engines like Minecraft or getting over it. However, it is insanely hard to do, and since Scratch has no physics engine, everything has to be programmed from the ground up. You have already read the title, so you might wonder how I got YouTube working in such a limited engine, which is missing half the basic tools you would need, like making web requests or rendering video. Before we get into this, I want to clarify that this video is not meant to encourage anyone to break YouTube's terms of service or endorse third-party clients, but rather showcases a proof of concept for educational purposes. With that, let's dig right in. You see, one day I stumbled across an interesting GitHub repository. It supposedly provides info on how to get HTTP requests working in vanilla Scratch 3.0. This immediately intrigued me, so I looked into it and it turns out it exploits a block from the Scratch 3.0 Translate extension, which uses a Scratch hosted endpoint to translate strings using Google Translate on the fly. The repository instructs to utilize the Windows hosts file to associate the Scratch Translate service hostname to localhost, making it connect to a local server of mine instead of Scratch's. I decided to try this with the sample server from the repository using a custom local certificate registered for Translate service with mkcert. And as you can see, this works. We can now get a response from any HTTP server online. However, this is a little more complicated to set up, so I had a different idea. I made a user script in TamperMonkey which will apply to Scratch projects. If the string starts with HTTP and a space, it will modify the request to point to a different target host, in this case localhost, under the same translate endpoint. And as you can see, we get the same result. This got me thinking that I want to try and port something interesting to showcase this. Well, why not YouTube, the platform you're watching right now? Now that I have the ability to make requests, I am able to modify the server to bring Scratch the data required to play videos. However, here comes the next tricky part. How do I render video frames in Scratch? After all, I cannot dynamically generate costumes for sprites or even transfer any kind of media through Scratch HTTP. With the translate block, I am restricted only to text. Depending on the resolution, each frame of a video has a specific set of pixels. For example, 144p video, say in 256 x 144 resolution, contains in total 36,864 pixels. Each pixel can be represented by its respective RGB value, which specifies how much red, green, and blue the pixel contains. While sending these pixels over as raw bytes will be great in theory, Scratch strictly enforces UTF-8 string rules, meaning raw binary data will choke or expand into a broken mess. To keep things clean and least headache inducing, I switched to transferring hexadecimal or hex color codes instead. If you aren't familiar, hex is just a base 16 numbering system using 0 through 9 plus A through F. While standard RGB expresses colors as 3 numbers 0 to 255, which take up in total 9 characters for a single pixel, Hex packs those exact same red, green, and blue values into a fixed 6-character string, saving us 3 whole characters per pixel. It is also predictable, 100% safe for text parsers, and natively understood by Scratch. For Scratch to properly parse these frames, we also have to provide information about how many frames are included, as well as the video's resolution, duration, FPS, which will all be prepended before the frame data, all fields being separated by a rarely found character, in my case this one. We are doing this because we are forced to separate fields in a singular string, as Scratch does not allow for multiple response fields. It utilizes a singular result1, as this is meant to be a simple translation endpoint. After our custom server downloads the target video in 144p resolution, it will process each frame with FFmpeg, extracting each pixel as a hex color code where the final string with hex values from all frames will be appended to the response. We do not need to use a delimiter for those frames, as every hex color code is 6 characters long, making for a predictable length when parsing. First, to the scene I will add a helper for making an HTTP request with translation block that will append the HTTP prefix required by the user script and utilize a random character to avoid using cache responses that Scratch uses for efficiency when translating. After that is done, I can add the initial code that will test server connection, ask the user for a valid video ID, request the video from our server, and if the request times out, wait a few seconds and try asking for it again until the server returns a proper response when it's ready. If Scratch receives a non-error string, it will then extract the initial info fields for the video, which I have called metadata, and lastly the frames themselves, each pixel of which is represented as a hex color code. Each frame is added as its own entry inside of a video frames list. We face a problem here. Passing all video frames in one string will become heavy and hard to process for Scratch very quickly. Not to mention the time it takes for the server to process them all is too much, especially for longer videos, so requests will almost always time out in Scratch. To account for this, we will pass only the first 50 frames in the first request, then make Scratch fetch the next one starting from the index after the last received frame until the server responds with end, meaning there are no more frames to be fetched. Additionally, let's limit total video length to 5 minutes as to not overflow Scratch with too many frames for longer video. Now that all the frames are loaded into our list, I will make a function which will play the video after it has been parsed, which broadcasts a render message for each frame, utilizing a timer to keep frames flowing properly. The render message will be accepted by a renderer object, which has just a single pixel costume and is used to, you guessed it, render the frames of the video. When it receives the message, it calls a render function that, according to our set rendering size, draws each pixel of the video from its respective hex value in the center of the scene. Using hex color code is also very convenient here, as the pen extension in Scratch supports it natively. We can just append 0x in front of the value and it will be set as the pen color, without us having to manually parse it. It's also important to ensure the render function has run without screen refresh ticked, as it will ensure frames show up on the screen instantly without us seeing how they get drawn in real time. If we try to load, say, me at the zoo now, you can see that the experience is like watching a PowerPoint presentation. It's nothing like the flow of an actual video, as Scratch cannot keep up with drawing all frames of the video, even if the render function works without refreshing the screen. Because of this, I have to heavily limit the FPS the video will have on the Scratch side. From what I have tried, 6 FPS is the best middle ground, so that is what I will use. We also have to add an additional field to the video metadata, which is the FPS timing or step between frames that Scratch has to pause for during playback, so that the video is timed as close as possible to the original regardless of the lower FPS. While it is slightly better, rendering speed is far from ideal for actual video playback. Even if the video is playing in 144p, the lowest resolution supported by YouTube, it is still too heavy for a makeshift Scratch video renderer. Let's try lowering the video resolution further. I will lower it from 144p to 54p, where the width of the video will be adjusted accordingly, depending on the aspect ratio in our extract frame function. Not only are frames processed by the server and parsed by Scratch way faster now, but the video also renders great on my PC. It is a noticeably lower resolution, but in my opinion it does the trick. Keep in mind, playback may still be slower on weaker devices. Now, you might say that this is only half of what actual video playback entails. After all, where is the audio? Well, Scratch does not have the ability to natively stream audio on the fly. Same issue we initially faced with video rendering. If only there was an extension which made network requests but specifically for audio. Well, guess what? There is! Right next to translate, we have text-to-speech, an extension that provides a speak block which requests an audio file from an endpoint under synthesis service.scratch.mit.edu.
Hello. What's up? This is how we can get audio working.
Let's also intercept that in our user script and list it under a synth endpoint on our server, which will return the audio file of the video that it would have downloaded earlier when the video was initially requested. Afterwards, we create a message in Scratch which will start the audio by using a speech block that requests the video's audio. The reason we use a message here is that it will let the audio play in a separate thread, meaning it can run while the video is playing. Otherwise, our whole script will hang at the speech block until the audio finishes. After all frames of the video have rolled out, meaning the video is over, we also do a stop poll to end the audio, because for some reason Scratch will only stop a TTS block if we stop the whole project. None of the other stop options work here. Next up, I added the ability to pause or play the video. When the video is paused, the whole project is stopped so the audio stops. When it's played, the frames start rolling from where they finished off, while the speech block requests audio starting from the calculated seconds from the current position of the video, based on the full video duration. To make this work, using FFmpeg, the server returns an audio stream starting from the requested time in the audio file. A drawback of the hack we use for loading audio is that it may not exactly be synced to the video, as we have no way of checking when it has been fetched. All of that is done internally through the save block, which we don't have control over in vanilla Scratch. Luckily, you can now pause and play the video until the audio syncs well. This play pause feature made it really easy to also implement a progress bar that we can use for syncing through the video. This can only happen when the video is paused though, as to ensure the audio has stopped. Using this feature, we can play the video from wherever we want, previewing the current frame while seeking around. Now that we have the base functionality ready to go, it's time to polish the project. I added some metadata to go along with the video, which is appended to the initial video data that is sent over by the server. The text is dynamically rendered in Scratch using a font sprite, where credit goes to GriffPatch for the ready-made costumes and most of the code used. I also added a top bar with the YouTube logo and a search bar, which is able to search for videos, displaying the first 3 results. This functions through another endpoint on the server, which sends over information about each video and its thumbnail in 96p quality, represented by hex color codes for each pixel, rendered in the same way as video frames. As a finishing touch, pressing the green flag to start a project no longer asks for a video ID, but instead shows 3 popular videos from the local country, which is curiously achieved by searching for a singular space. All in all, this is how I got a bare bones YouTube ported to Scratch, using a simple clever hack for enabling HTTP GET requests and tiny workarounds here and there. My GitHub repository with all required paths to run this is linked down in the description. I have not uploaded this project to the Scratch website, as I believe having to use a script to modify Scratch to get it running is not really in line with their TOS, which is why I suggest you do not do so as well. Otherwise, feel free to run the project yourself at your own discretion and modify it as you please, as long as you follow its license. I hope you have enjoyed this video, and if you have, remember to leave a like and subscribe if you'd like to see more random tech fun. Thank you so much for watching.